Okay, now we begin with today's lecture. Now, the first things I want to do is to say something about the homework assigned last time. Okay, so last time I assigned this homework, and this is a typical homework, typical problems involving special sequences. And during last lecture, we have already seen 2 examples. So I don't think there will be a problem with you. Okay, so I'm going through the entire process. So this is basically the solution. So first you need to show that this sequence is increasing and bounded. So of course, we're using the induction to achieve that. So you check the first case, n equal 1. So when n equal 1, so here we predict that the bounds is equal to 1, okay? So when n equal 1, you can see that because x1 equal 1/2, which is less than 1. And also we're going to show that x1 less than x2, but this can be done by checking. x1 equal 1/2, x2 equal what? x2 equal to you just plugging 1/2 into the right side of the formula, then compute. It turns out to be 17/24, which is greater than 1/2. So this is satisfied. Now you're making the assumption, the inductive assumption, assuming xn is always less than 1, and also xn plus 1 is less than xn. And then you begin to see, to go to the next level, you check the xn plus 1. Now, based on the formula, xn plus 1 equal to xn cubed plus 2 divided by 3. Okay, now because we assume that xn less than 1, so you can replace xn by 1. And then you can see that that will be equal to 1 plus 2 divided by 3, which is, okay. So therefore, the value is exactly equal to 1. So this means that the expression xn cubed plus 2 divided by 3 is strictly less than 1. So this shows that xn plus 1 is also less than 1. And then, since we assume xn plus 1 is less than xn, so you take q, then plus 2, then divided by 3, then the same relation hold. So this shows that xn plus 2 less than xn plus 1. So this finished the induction. So this induction have proved 2 things. The first thing is bounded. The other one is increasing. So therefore, by theorem 2.8, and the limit exists. Limit xn, let's call limit xn equal to x. Then you're taking the limit on both sides of the formula. You can see that this limit x satisfies the equation. So x equals to x cubed plus 2 divided by 3. So this gives x cubed minus 3x plus 2 equals 0. Okay, this 3 order equation with 3 order, right? 3 degree. So therefore, now how do you solve this equation? It's not a quadratic equation. So here you have to easily make an observation. You can see that 1, if you plug in 1 here, 1 is the solution. Okay, obviously. And now, next, very critically, and so once you know 1 is a solution, so you can divide the expression. I mean, divide x cubed minus 3, x plus 2, divide this polynomial by x minus 1. Okay, divide the polynomial by x minus 1, then after you divide, you get a quadratic formula. And then you look at the quadratic equations, you'll see 1 is still a solution there. And the next solution is minus 2. So for this equation, you have 3 roots, okay? The first root is a double root, that's x equal 1. The second root is a single root, x equal minus 2. Okay, so the limit has to be either 1 or minus 2. So obviously it has to be 1 because the sequence is a positive sequence. So a positive sequence cannot reach to a negative limit. So therefore the limit has to be non-negative at least. So therefore limit equal 1. So that's the solution. So this is kind of problem is very important. Okay, so You can see that in the chapter quick, there must be a problem like this will appear. Okay, so you have to prepare for it. Okay. Okay, so this is the problems, and now let's continue. Okay, the next thing is very important. That's 2D. Okay, the second. So previously we have criteria of convergence for the monotonic sequence, and we know that already. Now here we have begun to talk about the second criterion. That's the criterion for convergence with the Cauchy sequence. Okay, so in order to do that, we have to prepare a theorem. So this theorem is extremely important. It's called the Bolzano-Weierstrass theorem. And the theorem, the statement of the theorem is very simple. It's actually I introduced this theorem last time. So this theorem simply says that a bounded sequence, suppose you have a sequence which is bounded, and this bounded sequence always has a convergent subsequence. Now, the sequence itself may not be convergent, okay? It's just bounded. But however, as long as it's bounded, you can always get a subsequence out of this sequence so that the subsequence is convergent. Is a convergent subsequence. So boundedness is extremely important. Now, without boundedness, then this result obviously is not true. You're thinking about the natural number sequence, 1, 2, 3, 4, up to infinity. So this is an unbounded sequence, but this unbounded sequence will never have a convergent subsequence, because every convergent subsequence, every subsequence will go to infinity. But however, once the sequence is bounded, then the sequence always produces a convergent subsequence. Okay, the subsequence will be convergent. So today, one of the main things to do is to prove this result. And the proof of this result itself is very important because it's a very special way to prove the theorem. And the same argument is going to be used in the next in the later chapter. Okay, so the way how to prove this theorem itself is also important. Okay, so let's prepare to prove it. So let's say that you have a sequence xn, which is bounded sequence, okay? And very importantly, we have to, instead of looking at the sequence itself, now we have to project the sequence on the axis, the axis. So each term in the sequence is a number. So each number will correspond to a point in the axis. So that's what we are trying to do. Is we want to do the projection first, okay? And but you can see that the sequence of number will project it to the sequence of point. But these two things are not one-to-one, because, for instance, so let's say xn equals to 1. 你不要写啊。xn equal 1, so that's called will project to the point 1, right? Xn equal to 2 will project to the x. But you know that the xn may repeat itself, like x1 equal 1, maybe x5 also equal 1. So x1, x5, there are two different terms in the sequence, but however, they actually being projected into the same point. So projection is a one way. You cannot going back, okay, because of the repeated term may only project it to the same point. Okay, so let's make this happen. So let's consider a set X. A set X is all the numbers, xn. So we're no longer thinking about this as a sequence. The set X is a set. Okay, so you can see that so that a set can be expressed by a certain number in the axis, right? And you can see that the xn, their number can repeat itself, but the repeatedness is not going to reflect it in the x. X maybe have a fewer points than the terms. And especially the x can be a finite set. For instance, let's say xn is a constant sequence. Xn always equal 1, for instance. In this case, the set X consists of only one point. That's 1, right? Okay, so xn can be anything. The x can be anything, even though xn can be a very different sequence. Okay. So this is the first important things you have to notice from this approach. So now from now on, we are going to consider two special cases. The first case we're going to talk about is, I'll look at this set, okay, X. The X may be just a finite set. Now the sequence is an infinite sequence, right? Have infinite number of terms. The X can be a finite set. Just like previous example, let's say Xn is a constant sequence. Then the set X is just a single point set, okay? So you first need to think about it. What happens if the set X is a finite set? If it is a finite set, so what does it mean? That some term in the sequence repeats itself infinite number of times. This must be happening. Now, if none of these terms repeat itself by infinite time, then you can see that X has to be an infinite set, cannot be finite. So in the first case, when we assume that X is finite, so this means that the term Xn, some of the value in the term repeats itself infinite number of time, okay? Like say X equal like 1 repeats itself infinite time, maybe X1 equal 1, X5 equal 1, then X10 equal 1, X17 equal 1, and whatever, okay? Repeat itself infinite number of time. Now, if this happens, then you can see that you can automatically create a constant subsequence, which is convergent. Because if 1 repeats itself infinite number of time, so this means that there's an infinite number of terms in Xn. They're all equal 1. So those terms forms a subsequence, and it is a constant subsequence. So therefore, has to be convergent sequence, right? So this means that if we assume that X is a finite set, then we don't have to continue to prove it, because the result is obviously I can create a constant sequence immediately. No problems, okay? So we're going to consider the important case where the X is infinite set. Okay, F is infinite set. Now, as at the very beginning, we know that the sequence Xn is a constant, is a bounded sequence. So this says that if you project into the number to the x-axis, the set you are getting, the X itself, is a bounded set. Okay, it has to be a bounded set, right? But bounded set consists of infinite number of points. Okay, so that's the situation we're facing. Well, since it is bounded, okay, so therefore I can cover this set by a large interval, I equals minus n and n. N is a certain large number n, okay? Just like the graph shows that the interval minus n to n, and in between, there's a set X. So I'm not going to draw this set. Set can be very complicated. It consists of many infinite number of points between minus n and n. Okay, so now let's begin to see how we can handle this case. So what we're going to do first is going to divide I into two equal sub-intervals. Okay, in the middle, I divide the minus n to n. The middle point is 0 point, so I divide it into two intervals, left one and right one. Okay, now both intervals will involve certain points from X, will cover a certain point from X, right? And obviously, one of them must contain infinite number of points from X, or infinite number of X, okay? And this could be the left interval or the right interval. Now, you cannot have this situation that the both interval only consists of finite number of points. That's impossible. Then this will imply that the X itself consists only of a finite number of points, okay? So one of them must contains an infinite point. So let's say that I denote this subinterval by I1, which continuously contain infinite number of points. We call I1. I denote, let's say that the left interval is I1. That contains infinite number of points. And then the next, I'll do the same thing again. I divide I1 into two equal intervals, okay? And again, one of them must contain infinite number of points of x, okay? So we denote the second subinterval by I2. So this time, maybe I2 is a right interval. Okay, so every time I do the dividing, those intervals getting smaller, cut by half. But they still share one thing in common. That is, they are continuously contains infinite number of points. Okay? So I continue this to divide in this way. And then we get a sequence of nested closed interval IN. You can see every time from I to I1 and I2, they are nested. One contains the other, okay? So in dividing this way, I can get a closed interval IN, a sequence, which is nested, such that IN always contains infinite number of points for x. Okay, so that's how we are trying to find out how we can do to find the limits, the subsequence. Now, also another thing you have to be realize that every time we be making dividing, the size of interval gets reduced by half. Okay, so you can measure the total, the actual size of the IN. The actual length of IN is equal to n divided by 2n minus 1. So this means that the length of IN goes to 0 when n goes to infinity. Okay. So it goes to 0, right? Okay, so what we can do next? So what we're going to do is for each IN, so IN consists of infinite number of x. So you look at IN intersect with x. So there are infinite number of terms involved in the sequence, okay? Or in the small intervals, okay? So I pick one term, I pick one point which belongs to x from IN. I call this term is YN. And the YN itself will form a subsequence. Now here, there's some detail involved. I didn't print it out. So YN, so suppose I fix N, okay? I talk about IN intersect with X. So this is inside in this intersection, we have infinite number of points involved. I just pick one point. So this point will correspond to certain term in the original sequence. So that term, I'm going to redefine this term called YN. Okay, so YN is a term in the original sequence. Okay, so they are formed the subsequence. But remember, when we form the subsequence, I want to make sure that this YN, okay, is the order is increasing, the index is increasing. Okay, you cannot have a decreasing or a non-increasing order to get a subsequence. The index always increase, right? So here there's a trouble. Now once I determine the YN in IN, okay, now we determine the next term in the subsequence. That's the YN plus 1. The YN plus 1 should be choosing for the IN plus 1. Now, how do I make sure that the YN plus 1 is a later term than the YN in the original sequence? So that's one of the important detail. But if you think about it, you can see that actually it's a very simple solution. The fact is that the IN intersect with X, there are always infinite number of terms involved here. So let's say YN is choosing. Let's say the YN corresponds to X 100. The 100 is term, for instance. Okay. Now, how do I choose the YN plus 1 with the index greater than 100? It's easy because in the IN plus one, there are infinite number of terms involved. So I can always pick one term having higher index than 100, is of course. If all the index are lower than 100, so this means that IN plus one only involve a finite number of terms. That's contradiction. So because it's also still involving infinite number of terms, you can always make sure that the yn plus one is a later term than yn in the original sequence. Okay, so that's how we form this subsequence. Okay, so then we're going to show that this subsequence, now we get a subsequence, right? We're going to show this subsequence is converging subsequence. Itself is converging. And how do you see this? Now here is the point where using the nested sales theorem. Now you can see intersection of IN, okay? Intersection of all these IN is actually not empty because they are nested, it's closed interval, bounded, so therefore intersection is non-empty. So there is a one point in IN, but actually there's only one point in the intersection of IN because the length of IN goes to 0. Okay. So I pick a y from the intersection. So this means that y belongs to all the IN. Okay. So now I'm going to justify the limit, and we're going to show that the yn is actually approach to y. So for any given epsilon, I choose k large enough such that n divided by 2k minus 1 is less than epsilon. So of course I can choose k large enough to make this happen. Okay. So then for n greater than k, now since yn and y, they are both in IN, and the length of IN is less than n over 2n plus 1. So you can see the distance between yn and y is also less than the length of the interval. So therefore, the distance yn minus y absolute value is less than n divided by 2n minus 1, which is less than n divided by 2k minus 1, okay, which is less than epsilon. So this simply shows that the limit yn actually approach to y. The proof is complete. So that's the proof of the for this theorem. It's very special. Now in the next chapter, you are going to see a multi-dimensional proof of the same result, and also you're going to see a more general proof for a more general result. So they all follows from the same ideas. So understand this idea of proof is important. Any questions? Okay, so this is the somehow we call it a BW theorem, and we're going to use this theorem a lot later. Okay. Now there's a homework problem associated to that. That's number 9, the last homework problem. So number 9 says that suppose you have a bounded sequence. Okay. Then I know that based on BW theorem, this bounded sequence will produce converging subsequence. But maybe there are many converging subsequences. So each converging subsequence may converge to a certain limit, and all these may not equal, have nothing to do from each other. Okay, but now suppose every converging subsequence of xn all converging to the same limit. Okay, now this is an extra condition. Normally, when you have a converging subsequences, then the limit may not equal to each other. But this time, in this theorem, we assume that they're equal. Okay, using this fact, and then you can use BW theorem to show that actually the xn itself converges to L. So this is a very deep result related to converging subsequence and the sequence itself. But the condition is that if the converging subsequence all converging to the same limit, then the original sequence should also be converging. It's no longer just a bounded sequence. It's also a converging sequence, converging to the same limit. Okay, if you have time to think about it, and later I'm going to provide the solution on this. All right. Okay, so today, this is the one thing we want to talk about is a BW theorem. The next thing at the very beginning, we say that when we want to talk about BW theorem is because that we want to get a second criterion of of the convergence. Okay, so another thing we want to do this today, I want to introduce the Cauchy sequence. Now, Cauchy sequence is a special sequence, okay? And what we want to show that is a Cauchy sequence. The condition on the Cauchy sequence is a necessary condition for a sequence to be converged. So therefore, you can see Cauchy sequence is another criterion for convergence. Okay, so first we would like to define what we mean by a Cauchy sequence. Okay, now the definition is very similar to the definition of limits, but however, when we define the Cauchy sequence, we don't have a limit cell present in this definition. Okay. Now, what we mean by sequence is Cauchy sequence. Now, if for every epsilon greater than 0, there exists a positive integer k, okay, such that when both index n and m greater than k, then the term xn minus xm is less than epsilon. Now, remember in the definition of limit, the final inequality is xn minus x, but this time it's different. It's a difference between terms. As long as the index n and m is greater than a certain number, then the distance between terms can be made as small as you want. So this, if a sequence satisfies this condition, it is called a Cauchy sequence. Now the Cauchy sequence has nothing to do with the limit. At this time, we don't know whether the Cauchy sequence is convergent or not, because there's no limit involved here. It's just a kind of properties and held by the sequence itself. But later we can show that this Cauchy sequence is precisely the necessary and sufficient condition for a sequence to be convergent. Okay, now this is another extremely important result for the analysis. Okay, I'll show you why this result is important later. Okay. Now today our job is to see some examples of Cauchy sequence. Okay, and how do you verify a sequence is a Cauchy sequence? Let's think about this sequence, n over n plus 1. We're going to show that this is a Cauchy sequence. So what I mean by, so this means that you want to verify that the final inequality is less than epsilon, right? Okay, so this is what we can do. So for every epsilon greater than 0, so technically, I'm going to choose k greater than 2 over epsilon. Now 2 over epsilon, since epsilon is small, so this number can be a huge number. So I'll pick a k greater than this, okay? And then for both index n and m greater than k, then you're going to see that 1 over n and 1 over m, they're both less than epsilon divided by 2. So I'm making the technical preparation, okay? So I'm going to show that when both index greater than k, then the final inequality will be satisfied. Now, of course, there are some computation involved. So that's the final the computation. So you look at two terms, n over n plus 1 minus m over m plus 1. So you can see here we're dealing with two fractions. So you put the fraction in one fraction, you'll become n plus m. Now remember, when you make it the fraction, something cancel in the top. Okay. Oh, sorry. There's a should be minus. The plus should be replaced by minus. So on the top you have n and m minus m times n. So these two can cancel. But however, you'll have absolute value n minus m. Okay. But however, so this is if I replace this equal sign by less than, that will make sense, because replacing minus sign by the plus sign is getting bigger. Okay, then I adding 2 to it, to the top, it's even getting even greater. Okay, now on the top, I have n plus 1 and n plus 1. And then I cut this in the middle. Okay, I separate these two fractions again. Now, once I separate these two fractions, okay, they are still linked by plus sign, right? But the one fraction is n plus 1 over n plus 1 times n plus 1, in which I can cancel the n plus 1. So you'll get a 1 over n plus 1. And the second half will also follow the same rule of computation. It will give you a 1 over n plus 1. So that's why, so this difference is less than 1 over n plus 1 plus 1 over m plus 1. Of course, they are less than 1 over n plus 1 over m. And based on the previous preparation, they're both less than epsilon divided by 2, which is equal to epsilon. So this verifies that this sequence is a Cauchy sequence. Okay, it's a Cauchy sequence. So this is a kind of direct verification. So sometimes when we verify something is Cauchy sequence, and you need to do the direct verification. Now, in the homework section, I don't have a question regarding the verification of this Cauchy sequence, but this will be important. Okay, in the quiz, you'll have a similar problem like this. You have to verify directly it is a Cauchy. Okay. So let's see another example. Another example is this time is more complicated. The xn, the term itself looks like a summation of many terms, like 1 plus 1 half up to 1 over 2n. Okay. So anyway, I define a sequence xn. So we're going to see that this xn is a Cauchy sequence. Okay, so again, we need to do some technical preparation. So for every epsilon greater than 0, I choose k large enough to make this happen. 2k to the power of k greater than 1 over epsilon. Okay. And then you can see for both index m and n greater than k, then you can see that the 1 over 2n and 1 over 2m both will be less than epsilon because they are both less than 1 over 2k. Okay. Okay, so now let's see. So let's see, compare, look at the final inequality. So for the final inequality, I have to pick two index, m and n, both greater than k. Now, one of them will greater than the other. So let's assume that n is greater than m. Okay, then you can see the difference, xn minus xm. You can see xn equals to 1 plus 1 half up to 1 over 2n. Okay, and the other one is 1 plus 1 half up to 1 over 2m. So there are many terms in common. Once they subtract, they are canceled. So xn minus xm is basically equals to all the remainder term that's starting from index m plus 1 to n. The sum of all these terms. And all these terms, I can see that I can remove 1 over 2m out and times a partial sequence. That's 1 half plus 1/4 up to certain other terms. Okay. Then you can see the whole thing is less than 1 over m is less than epsilon. Now here's some detail. Now inside parentheses, so this looks like a partial sum of infinite series. Okay, and this infinite series begins from 1 half plus 1/4 up to infinity. I know that this infinite series is equal to 1. So the partial sum should be less than 1. So that's why the product with 1 over 2m is less than 1 over 2m. So that's why it's less than epsilon. Okay. All right. So that's again we verify that the sequence is a Cauchy sequence. Now the third one, the third sequence. The third sequence we're going to show that I have another similar sequence. Xn equal 1 plus 1 half plus 1/3, 1/3 plus 1/4, and so on, up to 1. So we're going to see in this case, the xn is not a Cauchy sequence. Okay. So for this purpose, what we're trying to do, I'm going to use the method of contradiction. Okay. Now suppose the xn is a Cauchy sequence, just suppose, okay. And then for epsilon, so suppose it's Cauchy sequence, then it satisfies the Cauchy condition, right? So I choose epsilon equal 1. And then the condition says that there must be a k such that for both index n and m greater than k, xn minus xm is less than 1. So such a k always exists. So again, let's assume that you have two index n and m, both greater than k, but I also assume that n is greater than m, okay? Then just like in the previous example, if you subtract, you can see that you are only getting remainder. So you have 1 over n plus 1 plus 1 over n plus 2 plus all the way to 1 over n, okay, which is of course equal to xn minus m, which is less than 1. Now from here, we're going to try to get a contradiction. So the key is letting n goes to infinity. If you're letting n goes to infinity, you see this partial sum starting from 1 over n plus 1, okay? The partial sign is less than 1. So letting n goes to infinity, you can see that the whole sequence, whole series, starting from 1 over n plus 1, then to the infinite number of terms to the infinity, is less or equal than 1. So that's a natural consequence of this, this inequality. So this simply says that if you look at the series, 1 over n, so this is something you learn from the regular calculus class, the calculus 2, the series, there's chapter series, right? So this series is called harmonic series, okay? So the previous result, you indicated this harmonic series is convergent, but actually it is wrong because we know that the harmonic series is divergent. So this will give us a contradiction. So this contradiction shows that this sequence xn is not a Cauchy sequence. Okay. So this is the things I'm going to present today. All right. Any questions? And in the end, I would like to indicate, say something about the coming quiz. Okay, the quiz. So let me stop sharing of this PowerPoint. Okay, and then I'm going to look at the notes. I'm going to look at the notes. Okay. So in the chapter 2 note, there's in the end there's a homework problem. So you are working with all these homework. So here, so for this quiz, okay, for this chapter 2 quiz, I'm going to closely follow with a variation of homework problem on this list. Okay, I will specifically tell you which homework you need to prepare. So one of the problem in the coming common quiz will be similar to number 2. Okay, it was similar. It's cover the limits. How do you handle limits using the technique involved with epsilon argument? Okay, and another problem is number 3. Number 3 means you have two sequences, right? And we're going to choose a combination will follow the same combination of limits. Okay, now this is a simple one. And in the class, actually, I show you there are some different one, right? And with some of the term are nonlinear term, they are involving x n squared, something like this. Okay, so you are not supposed to just looking at this exercise, and also you look at the example we have discussed in the class. Okay, so here. So you may want to spend time to prepare it. Number 2 and number 3, these two kind of problem. Okay, and in the next 3 problems, like the 4, 5, 6, there are some problem again related to the epsilon argument. So this kind of problem should also be prepared, and I can tell you which one is similar to the whole problem or to the quiz problem. Maybe similar to number 4. Or similar to number 5, something like this. Okay, so now so far I have talked about 3 problems, 3 possible problems in the quiz. Okay, and And then number 8 is important. I mentioned about this today. So number 8 is another problem in will appear in the quiz. Well, in the same format, okay, exactly in the same format, but the sequence will be different. Okay. So there, I'm going to prepare 5 problems on the quiz. So the last one, and will be a Cauchy sequence. So we have just talked about the Cauchy sequence. Okay. So this is the things you need to prepare for the chapter 2 quiz. So I'm going to finish chapter 2 this week. So in the Friday, on Thursday, we're going to finish the whole chapter. So the quiz, I was thinking about the quiz on the next Thursday. Okay, so that means on next Tuesday, I'm going to start with a new chapter, chapter 3. All right. So this is the some information about how you prepare for the quiz. Okay. Any questions? If no questions, so we can finish today. All right. Okay, that's it for today. Thank you.